Hi there. Today we'll look at an image is worth 16 by 16 words, transformers for image recognition at scale. So this paper is a bit special. Andrei Karpathy tweeted this out, and I'm going to guess many of you have seen it already. It's a paper that's under review at ICLR. ICLR, of course, uses open review, so all these submitted papers can be seen and can technically be commented on. And as you can see, it's anonymous. And good thing it's anonymous, because the double-blind review process relies on anonymity. So we can really evaluate this paper, which is a very interesting paper, at its merits without, having a clue who would be writing something like this. Now, out of pure randomness, I just happen to have this in my Control-C, Control-V memory. I just pasted this here. I don't know why, but this is this other paper called Big Transfer, General Visual Representation Learning by Alexander Kolesnikov, Lucas Bayer, Xiahua Chai, and others of Google Research. I've actually made a video about this, so if you're interested, totally not related at all. So disregard the fact that the paper that we're discussing here uses a GFT 300M dataset that is not available to the public, only to Google. That is, and actually this other paper also trains on that. Disregard that. Also largely disregard the fact that their model is called VIT, while the other paper's model is called BIT. Disregard the fact that they train on the exact same data sets, as you can see right here. This here is ImageNet, then C for 1000 pets, flowers, and the VTAB, this visual task adaptation benchmark. I've done a video on that too, by Google. But they do have actually the ImageNet Real here, which is just a set of new labels for ImageNet, which comes out of a paper by Google with largely the same authors as this paper. Disregard the fact that the color scheme for the VTAB evaluation is exactly the same as is the histogram plotting. And of course, we don't even want to bicker about the plotting style with these bubble sizes and so on. Anyone could do this. Anyone in the world could just randomly have this much overlap with these models, and of course anyone just has the money laying around to train on 2,500 TPU v3 days, and compare with 9,900 TPU v3 days for the BIT. I guess you could just pick those numbers out of the paper, but what do I know? No, don't worry. Peer review is totally fine. So I hope I've made my point. This is by these people, and people say, we need anonymous on archive because the danger is that people upload their paper on archive and then we can see who they are. I think this should prove to anyone that an anonymous archive is it's the crappiest. Why would you ever work against the core incentives of people? Clearly these authors have an incentive to make known who they are. And clearly we as readers have an incentive to figure it out. And to completely work against these incentives just seems it seems dumb, it seems counterproductive, and it doesn't work, as you can see. What do you want to do? Standardize the plotting styles? Standardize everything? Standardize the citations? Come on. Here, you go when we compare, oh no, where is it? When they compare against things, they say, oh, our first point of comparison is the randomly big transfer by these authors that we have no relation to, maybe or maybe not. It's ridiculous. You can't shield this fake anonymity. This is actually counterproductive, and it only helps the big labs, this anonymity criterion. All right, let's actually dive into the paper after this rant. Well, yeah, don't worry. Peer review, very pristine, very good, very anonymous. Double-blind, for sure. So the paper says, while the transformer architecture has become the de facto standard for natural language processing tasks, and we know this, this is from the first attention is all you need paper to things like BERT, GPT, GPT-2, GPT-3, transformers have revolutionized NLP. They say its applications to computer vision remain limited. In vision, attention is either applied in conjunction with convolutional networks or used to replace certain components of convolutional networks while keeping their overall structure in place, which is correct. In computer vision, convolutional networks have been so incredibly successful since AlexNet, and then of course ResNets being the major contributor there. I mean, even this big transfer paper right here, all it does is scale up ResNets and then feed in more data. So CNNs are extremely, extremely powerful in computer vision. We show that this reliance on CNNs is not necessary, and a pure transformer can perform very well on image classification tasks when applied directly to sequences of image patches. And they go on saying that they outperform CNNs while requiring substantially fewer computational resources to train. Well, substantially fewer in these regimes of thousands of TPU days is, something that is a bit ironic, honestly. But it's pretty cool. So what's the deal with transformers and images? Classically, transformers are, of course, models that operate on sequences. Specifically, actually, they operate on sets. So you'd have a set of words, which you can characterize as tokens, which I'm just going to characterize as bubbles. And then the transformer would somehow take all of these in and do something with them. And something, in this particular case, is attention. And attention is a quadratic operation, which basically means that you have to calculate the pairwise inner product between each pair of these bubbles, which becomes a very, very large task very quickly. You see, I even have trouble drawing. I think I drew this twice. However, this already with 5, it is many, many, many interconnections, and you can imagine that if you are in NLP and have a paragraph that's maybe 500 tokens long, you need 500 squared connections. So this one thing is the limitation of transformers. They work really, really well for NLP. However, they are limited by the memory and compute requirements of that quadratic attention. Images are therefore much harder for transformers because an image, of course, is a raster of pixels. And there are many, 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 many pixels to an image, right? So usually, ImageNet counts as a large images in computer vision applications, but even ImageNet are like, 250 by 250 pixels, which are small, by human standards. We are used to looking at, 1,000 or 2,000 pixel side length on a regular basis for it to be clear. I mean, even the rasterization of this PDF, you can see you will recognize it as blurry. And that's way, way more resolution than ImageNet images. So just the rasterization of images is a problem in itself, even for convolutional neural networks. But if you want to feed this into a transformer, you have to think that every single location here, every single pixel has to attend to every single other pixel, which the image itself is 250 squared big. So the attention will cost you 250 squared, which is impossible in current hardware, even for Google, right? Maybe they can do it, but So people have resorted to other things, doing things like only local attention, so only attending to the kind of area around them, which of course is the foundational motivation behind convolutional neural networks, is that you learn kernels that are local, and then you kind of slide them across and over the layers, across the layers once you go from layer to layer. So the first layer, this part might attend to like a cone around itself, and this part might attend around a cone around itself. But then in the next layer, the thing that attends in the same cone will have a larger effective receptive field, right? So in this, the receptive field grows by depth. However, transformers are able to attend within a single layer to everywhere. And this paper solves this by not going in the direction of, hey, let's do local attention over pixels, but they say, let's do global attention by simply going over image patches. So they divide the image into these patches, as you can see here. And one patch is, in this case, something like 16 by 16. They unroll these patches into a sequence, which is a in first instance, it's a set. They combine this with a positional embedding. So the transformers, naturally, they have no idea what is where. It's not like the transformer, in a way, is a generalization of an MLP, of a feed-forward network. In a feed-forward network, what you have is you have connections between these different inputs and outputs, okay? And these are fixed. So this node here will always attend to this node here with the weight that's specified by this particular connection. However, in a transformer, this W isn't a fixed number. In a transformer, this W is computed on the fly. So, and that's dependent on what these exact nodes are. And therefore, while the MLP knows where information comes from, the transformer doesn't. The transformer computes on the fly and therefore is permutation invariant. And that's why a lot of applications add to the inputs these so-called positional embeddings, where they simply say, look, this here is patch number 1, this here is patch number 2, this here is patch number 3. And you can do this in a sophisticated way. In images specifically, you can say this is position 1, 1, this is position 1, 2, 1, 3. Then you go on by saying this is 2, 1, 2, 2, and so on. Now, they in the paper claim that they've tried this and it doesn't help. It's much easier if they just say this is 1, 2, 3, 4, 5. And these are learnable embeddings. So you don't actually feed the number 1, but what you have is you have a table, and the table will have these indices 1, 2, 3, 4, 5, and so on, and each one is associated with a vector, and these vectors are learnable parameters. So whenever you say this is the first patch, what you actually do is you go here, you grab the vector to the number 1, and you put the vector along with the patch into the transformer. Now, the patch itself is still a small image, right? It's a 16 by 16 image. So you have to get that somehow into a form where the transformer can understand it. One way of doing it, of course, is simply to unroll it and say, gee, this is a 16 by 16. What's 16 by 16? It's like 256. I think so. I don't know. I guess it's 250. It's a 256 dimensional vector. However, they find that if they first put that through a linear projection, that helps before they put it into a transformer. So there is one single matrix, and this one single matrix is called E. In this case, embedding, haha. They take a patch like this, they unroll it. So here you have the image. You unroll it into a big vector. You multiply that vector with the embedding matrix, and that's what goes into the transformer along with the position embedding. In this case, we have position embedding, 7. You go grab 7 right here. You concatenate that here or add it, and you put that into the transformer. And from here, it's a standard transformer. This is just out of attention is all you need, standard transformer. And what you do is you have a special input. This is a learnable embedding. It's like the BERT embedding, the CLS embedding, and you take the output of this thing finally in order to classify. And this is just a standard classifier. So it's a really simple architecture except for the bottom part here. It's a transformer. One of the inputs is decided to be special, that is not associated with any patch, but is a learned input. The output of that particular dimension or of that particular input you take as a classification. Okay, so there are more outputs right here, but they are discarded, of course, because so in the last layer they're actually not even computed, I would guess. What in the last layer only this thing is computed, but in the other layers everything is always computed, right? So you have many transformer layers in here. Transformer layers are of course made up from these blocks right here. Sorry, not the embedded patches, but this thing. Okay, and you see the multi-head attention, that's the expensive operation. So the paper completely discards the notion of convolutions. They have a variant where they, I believe, replace this patch embedding here with a convolutional embedding, but I don't think it helps much. They really want to show that convolutions aren't necessary. And I don't want to go too much into the details of the paper because also it's also subject to change. You know, an open review, you can revise it and so on. But the experiments show, as you can see right here, that this visual transformer, this vision transformer outperforms the other, like the convolutional networks, by a pretty significant amount, often, like sometimes small, but sometimes also large, and costs less to train than these big convolutional networks, at least of this one other paper, right? So it costs less to train. Here you see, of course, if you go 16 by 16 patches, then that means you will have, so if you divide your image into patches that are themselves bigger, that means your sequence of patches will become smaller and therefore you're computationally more efficient. If you go with 14 by 14 patches, but also the H, I believe, is more layers. There is actually a table up here. Yeah, so the huge has 32 layers, and that has double the amount of parameters. All of that gives you a higher computational requirement, still lower than the big transfer paper. Okay, so the idea here is you train on these big data sets like this JFT data set. So you pre-train on that. This is a weakly labeled data set of 300 million images, and then you transfer to the other data sets, which just happen to be the same data sets that this paper used, plus the other data set that the same authors created after this paper came out. Don't worry about it. Okay. They also test on this visual task adaptation benchmark, and you can see that specifically in these natural images subclass, actually both of these models make gains, but then overall the visual transformer outperforms the conv nets. So what's the deal here? What's the deal with transformers? And that's something I want to talk about. I don't want to go too much into the rest here. Of course, you can visualize the attention. You can see it's doing something sensible. And you can visualize the positional embeddings that are learned, which is pretty interesting. And you can see that the positional embeddings come out pretty sensible. You can see where they pay attention to mostly, and it seems like this positional embedding, it largely recognizes where it is in the image, even though you never tell it, you simply let it learn, but it relates to other positional embeddings that are in the same row or column largely, and that's all sensible. You can see the filters it learns, so this is analogous to visualizing what convolutional networks learn. And you can see it does something sensible. It does something that we're very much used to. If you look at ConvNet visualizations, you'll see exactly filters like these. So it learns almost like the same thing as convolutional neural networks, right? But it's not specifically programmed to do so. Also, you can see as you increase the depth of the network, the mean attention distance, so the distance over which the attention goes, increases, and from like the middle of the network, you pretty much have global computation. And this is also like this is almost like the drawing I made of the CNN, right? Where you would have the different heads. So some heads would immediately at the beginning go out. A CNN in this case would look like a line. A CNN would look like a line that's like this. The additional benefit you get in the transformers is, of course, that at the very beginning, you can already pay attention to things that are very far away. You cannot do that with convolutional networks or when you use local attention. So all this branch up here, that's kind of the gain that transformers can make. They can attend to very far away things right at the lower layers. Yeah, so what's the deal with transformers? It seems like transformers are coming for everything. So first, attention was introduced in LSTMs. So LSTMs with attention were the cool thing to do, and I think still are in some places in NLP. But then transformers completely replacing LSTMs in NLP, and now transformers are coming for vision. They have been paired with vision, as the introduction here said, but now they are replacing convolutions. Sorry, they've been paired with convolutions, now they're replacing it. And here's what I think about this. So what you had in LSTMs and in convolutional neural networks were good inductive priors. So technically, if you think about it, if you have something like an MLP, a feed-forward network, like we looked at here, the notion should be that it could technically learn any function, right? A feed-forward network can technically learn any function, but it's kind of unstable and so on. You know, if you shift by a pixel, all the inputs are all weird and so on. So a convolutional neural network for images seemed pretty good because it has a good inductive prior. And the good inductive prior is that probably what one pixel cares about is its immediate neighborhood. And then what that neighborhood as a whole cares about is its immediate neighborhood, right? So that's sort of how we look at images. Like you integrate over small regions and then you connect the regions to each other and so on. So this is a very sensible inductive prior for images, as well as the LSTM for language. If you have a language, right, having an LSTM, having the inductive bias of let's first process this thing, then remember some general woo state, then go to this thing, and then incorporate that into our memory, what we already know, right? Then that kind of updates our latent belief, and then we go to this thing, and again we incorporate that. That's how we read, and that's how we do it. And so the inductive prior of this model is actually very, very solid. And inductive priors or inductive biases, the name already contains it. It's a bias. We bias the model towards solutions that we think in general are relevant, are useful, right? We tell the model, look, we know you could learn everything from data. No doubt about it. We have the theoretical results. You could do that. However, you don't have enough data. And we want to make it a bit easier for you. So we tell you that certain things like CNNs, like convolutions, generally tend to be useful. So we restrict the model and we bias the model towards a certain solution, or LSTMs. These are biases that we introduce in the statistical sense of bias, right? So these are biases that help the model become very good at task. However, now we are in a regime where we have lots of data. and lots of data. And we know bias. Why is it called bias? Because it will bias our estimator. Our estimator will not be the perfect expected value matches the actual underlying thing estimator. Therefore, we know that if we have enough data, a biased model will perform worse in the end than an unbiased model. It's only in the not enough data limit that the biased model can perform better. At least, I mean, I'm simplifying here, but now transformers come along, and transformers aren't another architecture. Transformers are basically a general compute thing. They're even more general than MLPs. Like, people think that MLPs, like this MLPs, are the most unbiased thing ever because everything's connected to everything. No, transformers are actually more general because not only is everything connected to everything, but these connections are always computed on the fly. So a transformer is like the most general thing there is in terms of deep learning that we have right now that we can train. Yeah, I'm making bold statements, but that's how I think about it. So if the CNN and the LSTM are more specialized MLPs, then the transformer is a less specialized MLP. And therefore, it's not necessarily in the architecture of the transformer that makes it so special. It's just the fact that it is a general computer, and we are now able to feed enough data into it such that it can actually learn the things. And it can not only can it learn the useful biases, right? We give useful biases, and you can see it learns the same thing as a convolutional network, or very similar things, right? It learns these filters and so on that before we would have given this thing here as like a wavelet filter. That was even before CNNs, we fed in like wavelet filtered things, and this thing would be on top of the list. So it can learn that from scratch. But probably this thing is not exactly a wavelet filter. It's actually something that performs slightly better, right? That we couldn't have come up with as a bias to build in. And that's why it works better, because it can learn almost the same things, but it can do so a bit better because it has that much data. So I believe the world is still open. Transformers aren't the end. Transformers are simply one general computer. There can be others. There can be something even more general than a transformer. And the world is still wide open to build in inductive biases that are actually better than CNNs or LSTMs. Also to build inductive biases in transformer, or if you go in the other direction, to alleviate. Because what you see right here, and in the formula, you see this pretty well. There are inductive biases in the transformer. And if I had to guess, I would say the ones that are to go next are the skip connections in here. Now, the skip connections are very important for us to be able to train these architectures. Because if you read the ResNet paper, the residual nets paper, that's kind of where the gradient flows back. The rationale is that you can go very deep, and each layer only has to kind of calculate the delta that you have to do to the input instead of transforming the input as such, and so on. It makes a lot of sense, but it is a strong inductive bias, and it pulls through all of the layers, as you can see here, right? All of like the skip connections is pulled through all of the layers. This is a very strong inductive bias, and we tell the network, maybe it's sensible if you only calculate the diffs in each layer. If I had to guess, this is one of the next big things to go. If we have yet an order of magnitude more big data sets, and we figure out how to train big networks without these skip connections. All right, so it's not like, as I said, it's not like transformers is like the very, very good architectures in the same sense that LSTMs and CNNs are very good architectures. It is the fact that transformers are so general, they are actually able to make use of the big data that we just now have, that we didn't have before, and of the big compute such that these inductive biases of the old models become unnecessary. Again, totally random. Check out this video if you're in the mood for a totally random, absolutely non-related paper to this. Tell me what you think in the comments, and definitely, keep an eye on this on Open Review. It's going to be very, very interesting. All right, with that being said, that was it from me. Bye-bye.